Welcome to the mind of a math teacher.
Hey, it is a beautiful day to find the derivative of logs. So here we go. My goals for this lesson are first and foremost to really understand the derivative of the natural log, meaning we're going to prove the derivative of the natural log first, and then we'll extend that by proving the derivative of any type of log base b of x being our generalization for logs. And then we'll go through examples of using these. Really, the examples are fairly simple in comparison, and we'll spend most of our time on these proofs here at the beginning. So here we go. We want to go through and prove that if we start with a function f of x equals ln x, the natural log or the log base e of x, then we want to prove what the derivative of that is. Now, as a little spoiler, the derivative is going to be 1 over x. That's what we're shooting for at the end of this. But it's going to be quite a bit for us to get there, and so you'll have to bear with me on all of the different ideas that are going to come into this. And it is a really good review of both the limit rules and the log rules, and kind of the complication level is pretty nice on this one. So one thing that we're definitely going to need here is this definition of E. So this is not something that we can really prove um, because it's a definition. So we're going to have to use that as a reference a little bit later in this proof. So here we go. I generally like to start out my proofs of derivatives by using the limit formula for derivatives. So f prime of x is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. Just enough room there. And then we'll say to ourselves, well, what does this f function actually do? It does ln of whatever I put into it. So when I put that x plus h into the function, I'm going to get ln of x plus h. So let's get this next line going. We got limit as h approaches 0 of ln of x plus h minus ln of x all over h. Okay, this is going well. Now, the next thing that I would notice right away here is this minus sign, and I would want to use my quotient rule for logarithms next to combine those logarithms together. And that'll combine into a quotient, into a division. So we've got f prime of x equals the limit as h approaches 0 of ln, and now here comes my quotient, x plus h over x. So I've combined that together, and I still have this over top of h, but I'm just going to write that out in front here as a 1 over h to make it a little bit simpler to work with and to see where we're going. Because in the next step, things are going to start to come together so that we can see why we have this definition of E over here in that remember box. So when I put the 1 over h out in the front there, hopefully it reminds you of another logarithm rule that we can do where we can take multiples that are out in the front of the logarithm and we can bring them up here as a power. So we're going to do that next. So now we're still going to have our limit as h approaches 0. Hopefully I have room for this, of ln of x plus h over x all to the 1 over h power. Okay. Now all of this is inside of our limit. Okay, so the next thing I think that I would like to do is actually think about a limit rule for being able to take things outside of a limit. So I told you we're going to be bringing back logarithm rules and limit rules. Well, here we have a rule about limits that when you have a continuous function applied to everything inside of the limit, we can actually pull that continuous function outside of the limit. And so that's what I'd like to do next. Now, you might have to consider for yourself whether natural log is a continuous function, but it is. So we can pull that out of our limit. So we have now ln of the limit as h approaches 0 of x plus h over x to the 1 over h. And you might start seeing how this is going to come together and get more and more close to this value of e over here. So next, what I'm going to do, I'll have to rewrite a little bit, ln limit as h approaches 0. I'm just going to rewrite the inside here. Instead of x plus h over x, I'd like to change that to x over x. So 1 plus h over x. And now you should really start seeing the similarities between what we have up here in our remember box and our definition of e and what we have down here on the bottom. Notice here we have a 1 plus something, and it's to the 1 over n as n approaches 0. Down here where we have 1 plus something, and it's to the 1 over h instead of the 1 over n. So what we'd like to do now is a substitution. We'd like to actually change this to what happens with n's instead of h's. And so I'm going to choose this object right here, the h over x. I'm going to choose that to be n. And we're going to need another page to do this. So let's just rewrite this on the next page to get ourselves going. All right, to go on with our new page, let's also make a substitution. Let's get a new variable because I'm noticing we have n's over here in our box in our definition of e, and we currently have h's as h approaches 0. But we can get this to look exactly like what we have over here in our box by doing a substitution. So let me show you what I mean. If we say let n equal h over x, then, well, what's that going to mean for h? If you think about it, we multiply by x on both sides, and we could get h equals n times x. Okay, so that would mean that 1 over h would equal 1 over nx. Okay, so that way we can substitute in for our 1 over h, and we can substitute in for our hx. The only thing left would be to substitute in just for h itself. So let's think about what happens as h goes to 0. As h in this first equation here goes to 0, well, you see how the n would also have to go to 0. So we can replace this h with just n goes to 0. So let's see what we have now. This is going to be ln of the limit as n now goes to 0 of 1 plus n to the power of, instead of 1 over h, we're going to do 1 over nx. Now, I'd actually like to take it one step further, though, and call this 1 over n times 1 over x, because that's going to give us a good result as we move forward here. So we have 1 over n times 1 over x, like that. All right, now, getting back into our rules, next we're going to use just a little exponent rule that when you have exponents multiplied together like that, there's another way that you can look at this. This is ln of the limit as n approaches 0, just a little rewriting here, of 1 plus n to the 1 over n, and that's what we want, to the 1 over x. And that's an important little distinction, an important move that we've made in this proof, because notice these sets of parentheses. This parentheses holds all of the stuff that we're doing the natural log of. And now that the 1 over x is outside there, it's actually also jumped outside of the limit because 1 over x doesn't have any n's in it. We can pull it outside of the limit as well. So now this 1 over x can have the power rule for logarithms applied to it. We can move that out to the front as a multiple. So now here's what we're going to have. This all equals 1 over x times ln of the limit as n approaches 0 of n plus 1, I'm just writing that the opposite way, to the 1 over n. And now you should definitely notice this has been the definition of e that we've been looking for all along. So replacing that part with an e, we have 1 over x times ln of e. And of course, ln of e, what's the exponent that I'd have to put on an e in order to get e as the result? Well, that exponent would have to be 1. So this is 1 over x times 1, which is just 1 over x. So what we've ended up proving is that if we take the derivative of ln x, we get 1 over x. And that is a really nice result. Now, in the next part, we're actually going to generalize this so that instead of just the natural log, we can take the log of any base and do the derivative of it. So let's look at what that would look like. So we want now to take the derivative of, in general, log base b of x. And it might seem like a really daunting task, but what we really need to do is just use the previous result, the natural log derivative, and we can get this done quite quickly and easily. It just uses some log rules. So, namely, the change of base rule is what we're going to want to do. Now, very often, people will use the change of base rule in order to change bases to base 10, the common logarithm. But you can also change the base to really any other base that you want using this technique. So when we have log base b of x, we can change it to log of any type of log of x on the top and any type of log, the same type of log on the bottom. And I'm going to choose to do ln as what I change the base to. So now I have the derivative of ln of x over ln of b. Now this is actually really nice because ln of b is just going to be a number. So I could rewrite this as the derivative with respect to x of 1 over ln b times ln x. Well, since this is just a number, I can pull this outside of the derivative sign and have 1 over ln b times the derivative of ln x, and we literally just proved what the derivative of ln x was. It's 1 over x. So our result is 1 over ln b times 1 over x, or 1 over x ln b. So what we end up with for a rule is the derivative of log base b of x is just 1 over x ln b. Now, because this b is inside of our logarithm, we would want to clarify that b has to be greater than 0 and that b cannot equal 1, because if either of those cases occurred, we would have a problem. We'd have this thing be undefined, and we don't want that. So we're just going to clarify that as the possible values of b before we move on. Now, here's examples. We'll start very, very simply, and these examples will move up to be more and more complicated as we go. So we'd already looked at this, we've proven it, and now we need to remember the derivative of ln x is just 1 over x. Very nice. And you might want to include that x cannot be 0 in a situation like this, but x couldn't be 0 to begin with in our natural log, so you don't usually have to worry about writing that when it's already the natural domain of the original function. So this second example is going to use the second proof that we did. We said that when we had the derivative of log base b of x, we got a result of 1 over x ln b. So in this case, the b would be 5, and our rule becomes 1 over x ln 5. Very nice. Next example. All right, on this one, you have to recall that any log that doesn't have a base showing on it is going to be the common logarithm, the log base 10. So this would become 1 over x ln of 10. All right, on this example, we have a minus sign there. But remember that you can take the derivative of each term in an expression separately, and then just have the minus in between your terms. So we can do this in steps here. The derivative of ln of x is just going to be 1 over x, and then we'll have minus the derivative of log base 7 of x is 1 over x with an ln of 7 down there. All right, in our fifth example, we're going to keep on putting some more things together here. So first, I'd like to do the power rule on these logarithms. I'm just going to take these numbers from the front and bring them up as powers before I take the derivative. And in taking the derivative, we will need to use the chain rule on examples like this because the log function is our outside function here, and then we have an inside function as well. So for our derivative, the derivative of the outside function, when we leave the inside completely alone, is going to be just 1 over x cubed, and then the derivative of the inside is 3x squared, which that will simplify in a minute. Plus, over here we'll have 1 over, leaving the inside alone, we'll have x to the 10th ln of 10. This 10 comes from the base 10 that was happening here, and then times the derivative of the inside function, which is 10x to the 9th. So simplifying this, we should get 3 over x, because the x squared will cancel out 2 of the x's on the bottom there, and we should have a 10 on the top here, and x to the 9th will cancel out 9 of the x's in that x to the 10th on the bottom, but we'll still have 1 x left, and we'll have an ln of 10 still left there as well. So there is our result. Now, moving on to our last example. So hopefully you noticed right away that these logs do not have the same base. So we're not going to be trying to do the quotient rule. We're not going to put these together. But I will do the same operation that I did on that last example, where I'll bring these values up as powers. This -8 is going to become a power, and I think I'll do the -2 as a power and change this to a plus in the middle here at the same time. So we're going to get log base 6 of x to the -8th plus log base 7 x to the -2 and so now our derivative, the f prime of x, is going to use the chain rule again. We'll have 1 over, leaving the inside alone, we get this using our rule, times the derivative of the inside, which would be -8x to the -9th, plus, similarly over here, we'll do the same chain rule idea, 1 over x to the -2 ln of 7 times -2x to the -3. So this example is just going to involve a little bit of algebra, putting things together. We'll have a -8 come in on the top. X to the -9th over x to the -8th, will you subtract those exponents? So -9 minus -8 is the same as -9 plus 8. So we'll have an x to the -9 plus 8 is x to the -1. So we'll actually put that x down on the bottom, and we'll have our ln of 6 also down there to keep it company. All right, so then we have plus, let's see here. Oh, we're going to want to change that to a minus, aren't we? So let's change that real quick to a minus, because this -2 is going to be coming up on the top. So minus, and we'll have a 2 up here on the top. And then for our x's, we have x to the -3rd minus -2. That's -3 plus 2, which is x to the -1 again. So we'll put that x down here in the denominator with our ln of 7 still down there as well. And we've put everything together into our final answer. So if you like this video, it helps me out. It helps it get in front of more people. I think that's the way YouTube works. If you comment on this video, then that helps you, because it will show me what other videos you'd like me to make, things that you'd like me to answer and help you understand. And if you subscribe, it also helps you, because then you'll get these videos much faster. You'll get them as soon as they upload, and you'll be notified of that. So have a great day and keep on learning.